All right, everyone. Our next presentation, we have Mark Bauer, VP Product Management at Anjuna. So Mark will present on data security and privacy with confidential computing. Mark Bauer has 2 decades of experience at leading security companies in the US, Australia, UK, and Germany. He is a noted expert in data protection, data privacy, and information risk reduction with patented designs in data security tokenization techniques. Before joining Anjuna, where he owns product strategy for advanced confidential computing, he headed product and business strategy for Voltage Security, acquired by HPE, and the Atlia hardware security model, HSM business at Hewlett Packard Enterprise. He most recently led product management for Amazon's payment cryptography business. Please help me welcome Mark Bauer.
Hey, thanks, Kyla. It's to be here at Encryption Consulting's event, and I'm going to talk about confidential computing. It's a new technology that's widely available now as a new way to provide security for high assurance workloads, especially highly regulated workloads in the cloud. So let's kick off. So many organizations today have been moving to the cloud, but many of them also struggle with those workloads that have been limited by either the sensitivity of the data or possibly the code itself. And this can be addressed with, as I mentioned, confidential computing. We're going to talk about this today. I'll introduce you to the topic of confidential computing, and I'll walk through a number of case studies, including some very interesting ones in banking and also a defense organization as well. So why are businesses that process these highly regulated data ecosystems and workloads still blocked from transformation? Well, fundamentally, it still comes down to security, and fundamentally attacks themselves cannot be easily prevented, even in cloud environments. And these days, when we are looking at this, we have to think about how do we reduce the impact of the breach itself, constrain that to the least amount of damage possible, or minimize the impact entirely. And traditional tools don't generally address this. There's certainly ways to try and limit things, but often it's looking through the rear vision mirror of a breach that's already happened, and at that point it is too late. And there's a fundamental risk here that is the root cause of this. In all compute, whether it's on-premise or in the cloud or at the edge, there's this unsolved problem that software alone cannot fix. And indeed, the new cloud tools don't actually solve it. And what it comes down to is this issue that while on the one hand, we might have data at rest protection for our traditional workloads and for putting data into storage, and we may have data in transit protection for moving workloads around and interacting with different systems and services. But fundamentally, when we need the live information, the real data to run analytics, which is becoming even more important these days with machine learning, we've struggled with data in use protection. And of course, there are technologies that have attempted to address this, and some do to a partial degree, like tokenization and encryption. But fundamentally, when you need to operate on data, perform mathematics, deep analysis, or use the live information, data and use protection has been difficult to do at scale, and we're not there yet with technologies like fully homomorphic encryption. So if we can solve this problem, it actually starts to introduce a new way to solve all sorts of different types of workload challenges with a much simpler approach overall to both data at rest and in use, as well as in transit. The challenge, though, is that if an attacker gets access to working memory, they may get access to things like secrets in memory. These could be credentials used to access systems, maybe to access something like a HSM or a tokenization system that's providing another layer of protection in my infrastructure. If I steal credentials or API keys, I may be able to do things like run an API call to decrypt data. And the list goes on. If I gain access to memory as a root level user, or if I'm an attacker with that level of elevated privilege, then I can do all sorts of damage. And of course, once somebody steals things like encryption keys for TLS, for example, then the data that has been encrypted under that mechanism could be at risk from secondary decryption. And somebody can steal encrypted data and gain access to it later. But of course, the other thing that's been missing from the equation of protecting data in use is the actual application code itself. And so once again, we've got this huge potential for exploitation across both the things like secrets, keys, and credentials, but the code itself, which might represent the intellectual property behind the business. Now, in industry, we've seen that the types of vulnerabilities emerge, and we'll continue to see these as zero-day exploitation risks. The challenge here is that too often, all lines of code present some kind of threat. And when there's a 0 day, organizations have to drop tools, attempt to patch like crazy to try and mitigate the threat. And in the Log4j case, there was the opportunity for exploitation and highly elevated privilege, which could have led to significant exploitation risks and data exfiltration. And this is just one example. We've seen attackers gain elevated privilege from either insider knowledge of systems, attacks through malware, and ransomware these days is often not just trying to encrypt data, but to exfiltrate it and exploit all manner of vulnerabilities, be it 0 days or humans in the process. And so there's an unsustainable problem here that all organizations face that can come back to attacks to things like data in memory, that can lead to huge secondary infections and risk. And of course, when we look at the types of attacks that we've seen over the years, of course, the human element is something that is often compromised first to try and get inside an organization, but it's to try and get that user to click on a link, which then gives some level of exploitation, which allows attackers to then navigate through the network. So when we actually look at the types of threats we see, quite often, these exploits happen because memory cannot be encrypted in use and cannot be given assurances over integrity at the same time. Now, as organizations have moved to the cloud and implemented hybrid architectures, moving away from those comfortable on-premise systems into more advanced and more agile and more beneficial systems, particularly when it comes to cloud-native ecosystems that offer huge benefits of agility and scale, the attack surface that goes with this dramatically increases. And even if we just look at things like keys used to protect connections or data inside microservices or even API credentials, then the attack surface per all of these microservices massively explodes. And this becomes hugely problematic because just one chink in the armor can result in compromise across all manner of downstream systems, creating all kinds of compliance violations and possibilities for data leakage and breaches as a result. And of course, organizations are still somewhat skeptical of the shared responsibility model when it comes to those super sensitive workloads. While the clouds do provide fantastic infrastructure to build on, scale on, and to provide the undifferentiated heavy lifting that's needed to get business applications launched quickly, that comes at a cost. For the most part, while they provide the infrastructure layers and the assurances over its availability, the fact is that you, as the data owners, still have the full responsibility for compliance and risk. And that comes down to fundamentally the liability associated with your customer-owned applications and data processes, all that data that moves into third-party environments with third-party risks that go with it. Now, in a cloud environment, once you've provided that information back to the cloud provider, ultimately, when software solutions are being used to protect it, that is potentially accessible to the clouds themselves. And while they put many controls in place to mitigate this, fundamentally, you can't avoid this risk. And it's a very complex challenge to address in only software solutions. So I'm going to introduce you briefly to confidential computing. And this is a technology that has emerged over the last few years to address exactly these types of problems. It's to address the threats that we see to cloud infrastructure. It's to isolate the clouds from your infrastructure and your data operations so that there is no potential for insider compromise from the cloud itself. And it's available across the board. But let's have a look at what this actually looks like. And it may be familiar to you today. So in your wallet today, you probably have chip card technology. And in your phone, you probably have a smartphone. Now, the chip cards themselves are actually a confidential computing environment. You've got a hardware security chip that is designed to resist attacks and copying, and it actually runs software. So when you insert that chip into the reading terminal, it's powered up, it runs an application, it verifies things like signatures and so on, and it then creates essentially a trusted ecosystem to then transfer and convey information to an upstream host. That's often used to share and encrypt things like PINs for debit card transactions or identity information when presented to an identity verification platform. So this is a computing platform that's highly trusted, has been proven in industry for many years, and literally sits in your pocket. On the other hand, the mobile phone has a secure processor as part of its own internal infrastructure, and its purpose is to allow things like the biometric data, like Face ID and so on, to be secured completely independent of Apple and their cloud backend. And so should your phone be lost or stolen, then Apple has no means to gain access to it. It can deny subpoenas under law enforcement as a result, and it puts the control back to you, the data owner. And so this type of technology has been propagated throughout the clouds. And in fact, it's the core chipsets that have been enabling cloud delivery now for some time, starting with Intel SGX, a enclave chipset that was developed about 5 or 6 years ago. And since then, each of the major chip vendors, from AWS with its AWS Nitro Enclave platform, ARM with its ARM Realms systems, AMD with AMD SEV, and NVIDIA now with its confidential GPUs, creating hardware chipsets that allow workloads to be isolated, to have data confidentiality, data integrity, and code integrity at a hardware enforced layer. And so this is creating a very different way to isolate and protect workloads from all manner of attacks, be it external threats or insiders, with very profound implications for cloud computing. So in effect, this is a way to address this data in use protection. So when we think about that, what actually happens behind the scenes in these chipsets is hardware level protection of memory during use. And so the actual exposure of memory, code, keys, secrets, APIs, credentials, all manner of things that you would normally process in regular processors can be handled inside these enclave and isolated environments. And as a result, we can then start to think about how we can extend this protection to easily address data in use, data at rest, and data in transit through a single approach to protection. And so data in use protection here means that if an insider gains access to memory, if they are a privileged root user, or if there's malware or an attacker, all they see is strongly encrypted memory that's actually bolted into the hardware itself. And it's essentially an immutable infrastructure with new levels of protection. Now, of course, this is a technology that is in fact available across the clouds. As I mentioned, AWS has its Nitro Enclave technology, and it's something that you can actually utilize and acquire without increasing costs from a CPU standpoint. The challenge is how you actually use this for regular workloads. Similarly, with the Intel SGX platform in Azure, with AMD SEV in Google Cloud, and so on and so forth. All of the clouds have these chipsets available. It's now about how do you deliver a software layer to make this easy to accommodate to load any kind of application and run it in these kinds of environments to give it the level of protection that I've just described. So if we do that, then we can start to think about this hardware level of security isolation in our cloud environments using the processes that are already there. And this then eliminates this issue that admins have access to the back end, to applications. You can isolate one workload from another. You can isolate container to container, and you can start to build security barriers around workloads without having to really do a lot to the applications themselves. And this is almost giving you this almost instantaneous levels of protection for workloads as they run in a cloud environment. A very powerful technique that's been unprecedented in industry until this point. So our view on this is that in order to explore all of these capabilities in the cloud, all of these really powerful processors that have varying architectures, big differences between SGX and AMD SEV and AWS Nitro, well, fundamentally, rather than trying to re-architect each of these environments, which is extremely complex, we allow, and our view on the world is to allow organizations to take applications as is, run them in these environments at runtime, deploy them essentially where they're needed, where security is required, and to do that in short order. And of course, the fact that this is actually using hardware in the clouds directly, you see minimum impact on applications. In fact, we can exploit the full elastic capabilities of the cloud with full protection of both code and data at the same time. And so when we think about this, we also need to make sure that we don't just protect data in use on its own. We extend that boundary of protection so that any kind of data that's processed by these ecosystems remains protected under the control of these enclaves and hardware security systems. And last of all, of course, the reason organizations often use the cloud is for its elasticity and scale. The fact that we can adapt very quickly to market conditions or workload conditions on the fly. And traditionally, security hasn't always allowed that to be an easy process with manual inputs. So here we have a technology and a platform that allows you to scale elastically to wherever you need to be, where the processing is required to any level. So I'm going to quickly shift to a quick demonstration of this. Bear with me 1 second. So what I'm going to show you here is the Anjuna platform enabling applications to be lifted and shifted into these types of hardware enclave environments. In this case, I'm going to use just an Azure environment, but it could be multi-cloud, it could be a blended environment, it could be an AWS or GCP for that matter. So in effect, think of these simple applications here to illustrate this point. So I have a typical application that's going to enter some data in a browser. That's going to pass over TLS into this environment, which is an Nginx web server, up to an app server, again over TLS, and into a database. So let's see how this works. So here we have an example for somebody that's applying for perhaps a loan, a particular individual that wants to buy maybe a social network. So if I throw that data in through the browser, of course, it's gone over TLS from the consumer's mobile or web infrastructure, and now into this web tier here running Nginx. But if I'm an attacker that's managed to get root level privilege or elevated access to this server, or if I'm an insider with administrative rights, then there's all sorts of attacks that I could potentially run. And even if I grab memory, for example, by grabbing the process and doing a memory dump, then of course I can get that information that you just saw entered in the browser. Similarly, if I want to modify the executables, the actual code itself, then I might want to substitute some libraries with my own that allows me to steal data later on. This is a common attack we sometimes see in web servers, where the attackers try to hive off data, much harder to detect later on. We might want to also attack the operating system here, or pull a key out of the initialization files for decryption of TLS traffic. And yes, in practice, I might use a hardware security module here, but I think you get the point that if I have this level of access, then I can pull keys, secrets, and all manner of data out. So for a second here, I'm going to just stop this Nginx service and relaunch it inside, in this case, an Intel SGX enclave. Now, again, this is using the hardware already in the cloud. We're just making it possible to run the entire application with this single line here. So essentially what I'm doing is I'm taking the Nginx server, its configuration, and running it inside an enclave. And in fact, what we do is we package up and encrypt all of the code and data suitable for execution in this new hardware protected environment. So now the entire system here has essentially been packaged and virtualized and is running in a hardware-assisted enclave with memory encryption. So now, even if I attempt to extract the key, as a root user, I have no access to the inside of the enclave. If I try to dump memory, I can still pull the process, but the memory is encrypted by the processor itself in hardware. And now I get nothing. I'm just looking at, in fact, an encrypted memory. So all of those types of attacks have essentially been mitigated simply by re-executing this inside an enclave. Now, as the data moves across to this app server, of course, I can do similar types of attacks. I could scrape memory, getting this personal data here once again. I could even manipulate the code, maybe even steal something like an AI model or machine learning set of algorithms, might be intellectual property. And of course, I can still extract things like TLS keys if those are bootstrapped for booting the application from scratch. And that's another challenge. When you start applications like a web server or an app server or database, quite often you have what's called the secret zero. This is this bootstrapping credential to allow it to pull things from maybe a secrets vault or talk to a HSM. And without this level of protection of doing this in hardware, that type of credential is always potentially at risk and exploitable. So once again, I'm going to stop this server in this example and restart it and run it in an SGX environment. This could be an AWS Nitro equally, but in this case, I'm running all of these in an Azure SGX ecosystem. So now again, when I run these attacks, we get nothing. And in fact, I get no access to the code because actually all I see is encrypted memory when I try to dump it. Similarly, when I get to the database, once again, I could run an attack if I have that level of privilege, gaining access to things like temporary files, memory access to the database itself. Similarly, now I can then restart this and run it in an enclave. And so what I actually have here, from the browser all the way up through the web server, I'm going terminating TLS inside an enclave, now extending that to the app server, which itself is in an enclave in hardware encrypted environments. It's going up to the database, and we're going from enclave to enclave to enclave. So I've been able to very quickly go from unprotected applications to a protected environment that mitigates all sorts of attacks from insiders and external threats. So let me switch back to the presentation, and we'll just quickly walk through a couple of other points that are important to understand before we talk about some of the use cases. So I just described an environment where we are running an application at runtime into an environment that provides data in use protection, data at rest protection, and transport encryption, essentially hardware backed. So the question becomes, well, how do I know that I've actually done that? And how can I give assurance that the application that's running is the one I expected, and that the data that it's processing is only processed by that trusted application. So confidential computing solves this type of risk, and it's a process that is called attestation. And so this is kind of the problems that one of the problems that it tries to solve, and it solves it very well. So when you think about bootstrapping an application for that very first time, typically in the old days, we would actually have manual entry of things like smart cards into a HSM or keys being entered manually to start a secure process up. And of course, that's an untenable process and will never work in a cloud environment. And so then we start to move things like keys or environment variables with secrets to some kind of storage in our ecosystem. From there, we sometimes think about, well, how do I protect that? Maybe I can put them in a secrets vault. And then the question becomes, well, how do I access the secrets vault? And so then we might use a HSM for some of those root level secrets. And the question becomes, well, how do I protect access to the HSM with the tokens that I'm going to use to automate that at boot time? And so this problem starts to turtle down forevermore. So attestation in confidential computing uses hardware-backed keys that are actually fused into the processors to provide this hardware root of trust in the ecosystem. And so for the very first time, we can use these types of technologies combined with what's called measurements of the chips, the software, and the software environment to almost create a biometric signature for machine identity that allows it to identify itself to things like key management systems to then retrieve secrets into the enclave. And so we've never had to kind of compromise this system by enabling environment variables or manual entry of cards into systems and all of the horrible baggage that you have trying to manage that secret zero problem in the traditional way. And so you've got this huge capability here to automate how workloads can start without compromise from a security perspective. So very powerful stuff indeed. And so how do organizations use this? So confidential computing, of course, can address a whole gamut of data risk and data protection use cases, from the traditional compliance challenges to protecting things like analytics and machine learning workloads, both code and data. But it can also introduce brand new ways to do computing that were not possible before. So for example, when we have an organization that is looking to have data shared across different parties, this is what's called multi-party computing. And in many cases, you may not have the any kind of trust between those parties. So if you want to share data, the concern is that data may actually leak across them. And if they're two competitors, for instance, that want to share data for market level analysis, for instance, in financial services, then certainly that's not something that will happen with traditional techniques, even with encryption. But with an enclave, with a confidential computing based mechanism, organizations can create a space where they can load data, load perhaps a machine learning application and model, and then run that workload and get the results without exposing the data to either party. A hugely powerful technique. So it has multiple use cases, from anything from modern Web3 to key management in protecting keys and secrets that were traditionally in software, AI, multi-party computing, and the list goes on. So who is using this today? So we see this application across anything from the modern Web3 organizations that want to protect things like the keys and secrets used during blockchain validation and digital signatures. If one of those keys becomes compromised, then that can have a profound impact on the trust of that ecosystem. So when we have huge amounts of transactions going across these types of environments representing billions of dollars in asset value, trust and secrecy over those processes is absolutely critical from a key management perspective. And confidential computing is a very elegant way to solve this in this distributed environment where traditional HSMs probably don't play as an important role because of their centralized nature. But of course, organizations can use this for more traditional techniques, like moving mainframe workloads up into the cloud, for example, where the controls equivalents of the on-premise mainframe environment can now finally be realized and duplicated in the cloud in a hardware and backed system. And so this is a fantastic way to move those sensitive workloads that are often blocked for many, many years. And of course, when it comes to things like machine learning and analytics, then getting access to results really quickly. So being able to process analytic data on the fly in a confidential computing environment so that only the results emerge and that the personal and sensitive data stays essentially locked in this environment can lead to some very interesting and novel approaches for new analytic workloads. So lastly, I'll leave you with a pretty interesting case. One of our early customers in this domain is the Israel Ministry of Defense. And so their challenge was to move highly sensitive analytic workloads up into their cloud environment. These are kinds of workloads that require vast amounts of computing to provide real-time results from all manner of types of information coming into this environment. And so, of course, the challenge here is that you have extremely sensitive workloads. And ordinarily, these would have to be managed on-premise. But given the performance requirements, that was essentially impossible. And so they used Anjuna as the software layer to allow these workloads to be very quickly lifted into the cloud, allowing very swift results to come back with the maximum assurance that the information is not accessible to the clouds themselves, as well as to insiders inside their own organization. And so providing powerful results with minimum access and maximum security almost instantaneously. So to wrap up, we've certainly got a technology here that provides a very new way to handle this risk of moving workloads to the cloud. And for the very first time, to truly protect data in its native form in use, as well as at rest and in motion. And that's for application code, data, keys, secrets, models, anything that can be put in the enclave environment. And this allows you to unblock cloud transformation, whether it's traditional applications or moving more modern Web3 environments into these ecosystems on a very reduced risk basis, reducing the risk of threats, simplifying compliance, and reducing that dependence that you might have on patches in more exposed systems. Because essentially, we've isolated the soft underbelly of the software from compromise and exploitation. And of course, it starts to enable new business models, simplify the way that you can actually collaborate and share on data, and unlock new ways to access perhaps advanced analytics and machine learning. So if you'd like to learn more, you can certainly connect with us online. You can reach me here, both on LinkedIn, or you can drop us a line throughout this conversation here. And now we'll be happy to have a look at some of the questions that have come through.
Hi, Mark. How are you?
Hello, I'm great. Thank you. I'm just taking
Thank you very much.
Go ahead.
Yeah, sounds good. You look good. Sounds good. We've got a few questions that have come in here regarding your presentation. What are the implications on development and AI where they need direct access to hardware?
So, you know, when you look at the kind of the AI type use cases, you know, when organizations are dealing with personal or sensitive data, first of all, they have to think about what they have to collect from a legal perspective, you know, what they're allowed to collect and manage, first of all. But when there are use cases when organizations need to have access from a data science perspective, on a business need perspective that's allowed by compliance, to live data to running analytics, particularly for things like developing very strong machine learning models. Because if you're developing them on data that is either inaccurate or doesn't represent what the actual live data really truly means, then you can get very inaccurate results out of that, and you may not discover the true value of the solution of the information itself. And so, being able to lock down an environment in hardware that's already present in the cloud, so it's not like somebody's having to implement hardware to do this, allows data scientists to then run models, maybe to run their own analysis to build models and execute them in a very, very isolated environment that is separated from the rest of IT, root users, and the clouds themselves. And so this is kind of a new way that you can provide privacy over the information during processing for that science purpose, for the building the models and so on. So that's one of the use cases that tends to pop up pretty quickly.
Okay, thank you, Mark. I have another question here. Do you support legacy technologies and versions like PHP 7?
So we are agnostic of the underlying platform. And so organizations that are looking to lift applications to the cloud, move workloads up, and achieve compliance and isolate from the risks that we've just talked about, that's exactly what we enable. So when you think about legacy applications, sometimes it's very difficult to retrofit them with security. And so being able to do this at essentially at a layer which is almost like a virtualization approach. The best way to think about Anjuna is we're like a virtualization layer for confidential computing processors that are largely available in the cloud. So you can then lift an application into that environment, be it a database or a web server or an app server, and it gets the benefits of the hardware protections during use, data at rest protection as we implement it because we're virtualizing all of the storage. And then the network connectivity can also stop and start inside the enclaves themselves that we essentially allow organizations to create. And so we're agnostic of the underlying technologies. Now, obviously, there's always certain cases we need to look at in terms of things like any impact and architectural considerations and operating systems underneath. But would love to look at that because we can help companies move things very fast into these secure environments.
Okay, and here's a kind of a specific question. If we had an application in AWS, how long would it take to run it in an enclave? What would I need to do?
So the typical steps are, number one, we'd have a conversation about the nature of the application itself to look at what needs to run in an enclave and what could optimally run in the enclave environment first. That's a fairly straightforward conversation process. Then it comes down to downloading the software from our portal. So it's software that you run in a customer's cloud, in their virtual private cloud. The customer would essentially select infrastructure with the Nitro enclaves in AWS. And then they would use our tool to, at runtime, take the code and run it in the enclave itself, or run each component in enclaves. So it can be done very, very fast. And typically proof of concepts that we do to kind of dip a toe in the water, that is, can be done in just a couple of days, or sometimes for organizations with more complex apps, maybe 5 days to 2 weeks.
Okay. Do you see any performance impact with memory encryption?
So just to keep in mind, essentially everything is done in the hardware itself. So we are not doing memory encryption ourselves in software. The actual memory encryption happens in dedicated processors in the actual CPUs. And so that runs at full memory access speed. There isn't actually an overhead to that. So largely, you're getting the benefit of that in-use protection without performance impact. And in fact, the architecture that we provide allows organizations to take full advantage of the processing power of the cloud, whether it's a Kubernetes distributed application or a more monolithic application. And largely that will run at the full speed that the processor allows them to. So very little impact despite this massive benefit.
Okay, another one just came in. Can this work with Raspberry Pi joined in a cluster? or something?
That's a really interesting question. So when you look at the challenges of confidential computing, you do need the chipsets to be able to run that have this support capability. So Intel has SGX, and it has a forthcoming TDX architecture. AMD has what's called AMD SEV. AWS has AWS Nitro. So all of those are slightly different, and we make it look the same. Now, in the embedded world, ARM does actually have what's called ARM realms. I see this as having applications in the edge in the future, but right now we're focused mostly on organizations that are running these things in the cloud. But certainly, the embedded chipsets, not necessarily those that are in Raspberry Pi today, but those that maybe in the future might have this capability. And indeed, we see confidential computing being almost a ubiquitous capability that every CPU will have in the future. And then it will be a question of why are you not using it, given the massive benefits in risk reduction. And so anybody tinkering with Raspberry Pis today may see this start to emerge in these types of platforms, maybe in a year or two.
Okay. How does this compare to what the clouds offer directly?
Yes. So all of the clouds today, be it GCP, Azure, AWS, or for that matter, AliCloud in the Asia Pacific region, have chipsets available that you can consume and use. So you can utilize an instance, and you'll have an instance type that you can choose that has some of these processors. And of course, the clouds themselves do provide some of the very basic functions so that you can use them. But if, for instance, you're going into AWS, trying to convert an existing app and re-architect it for Nitro is a difficult challenge. You might be able to build your own Hello World app, but running multiple apps in this environment can be very complex. And certainly, Azure has introduced some new capabilities recently, but they tend to be at that sort of building block level, or introduce perhaps trade-offs with regards to security. So we take a view that you can't do either of those. It has to be a very simple process, but without trade-offs. So hardening the operating system, allowing it to just run an app straight away. So yes, certainly it's great, and we exist because the clouds have implemented some of those building blocks. But just as you would maybe many years ago, you probably wouldn't have written your own VMware, even though there was the building blocks in the processors and in the BIOSes. You needed that third-party layer to make this simple and straightforward to use. That's what we are.
Thanks, Mark. And the last but not least, I know I saw Dana mention in there, but can we try it out?
Yes, absolutely. So there's multiple things we can do. If anybody's interested in a demo, we can show this in literally 5 minutes. I think there was the demo in the showcase, but there's just a simple example that we showed today. But we certainly do also offer trials and pilots and things like that. So more than happy to try it out, kick the tires, test us.
All right, fantastic. Well, Mark, I hope you'll keep an eye on the comments, and anyone that's interested, please reach out to Mark and the team. Mark, thank you so much for your presentation, and thank you for your time today with us live. I really appreciate it.
Thanks, Kyla. Take care.
My pleasure.